Thank you, Ambassador Chen. I've taken my task this morning to try to provide some grist for a discussion of big data and big cities. I will try to paint the current landscape, some vision of what the potential is at the intersection of these two themes, and talk about some of the issues that we face as we try to realize that potential. Some of my remarks will be in the context of CUSP, the center that is now 2.5 years old that we're standing up in New York City, concerned with these matters. And you'll find also as I go through it that I will echo and amplify some of the points that have already been made this morning with no prearrangement with the other speakers, so some convergence in thinking. I think the first thing to understand is to get the slide advance to work. Is that urban data is not a new subject. The data have been collected about cities for millennia. The word statistics comes from the Latin word meaning of the state. And of course, the Romans needed to measure what was going on in their cities in order to manage the empire. But up until the last decade or so, the sparseness and quality of the data that we had about cities has limited the application of that data and limited the scientific understanding that we can extract from it. It's proven difficult to measure the urban system, to test hypotheses, to predict and monitor the results of interventions. But the new technologies that have already been mentioned are completely recasting the way in which we can study cities. The digitization of records, the proliferation of sensors, the analytical techniques, the computing power, they're giving us a view of cities with unprecedented granularity, variety, coverage, and timeliness, making the study of cities a completely different subject. I like to say in many ways it's like when Galileo first turned the telescope on the heavens, or Van Leeuwenhoek first looked at a living cell in a microscope. I'm trained as a physicist, and so my bias as I look at these matters is to want to know what can I measure with what precision and how can I use it. I like very much this quote from Lord Kelvin: when you can measure it and express it in numbers, you understand what you're talking about. As I've gotten deeper into the subject, I've come to appreciate, to some extent, the opinions of some of the others that say this is really about people and you need to understand that as well. And part of the challenge as we go into this is to meld this quantitative analytic approach with a more nuanced understanding of people. When I got into this subject about 3 years ago, a bit more, I asked myself as a physicist, what does it mean to instrument a city, as I would instrument any other natural system? It turns out you want to know about 3 categories of data. You want to know about the infrastructure, its condition, and its operation. You want to know about the environment, meteorology, pollution, flora, and fauna. And most interestingly and most problematically, you want to know about the people. If you were to ignore the privacy constraint, and of course privacy is central to what we're doing, but let's put it aside for the moment. You'd like to know relationships, locations, economic and communication activities, nutrition, health opinions, and so on. And the underlying belief in much of what we're doing is that if we can properly acquire, integrate, and analyze data in these 3 buckets, we can take government beyond imperfect understanding. Better operations, better planning, better policy. We can improve the engagement of citizens with their government. We can enable the private sector to provide new services for citizens and for governments. And most exciting for an academic, we can change social science and go from surveys that cover perhaps 10,000 people at most to sucking up data with great granularity, almost in real time, on 1 million people at once. It changes the business. It's no longer the hypothesis testing, randomized control trials, but it's just watching and learning. That's a mode that's not unfamiliar to some sciences, astronomy and earth science being the most obvious, but it's really different for the social sciences, who I think have developed a discipline appropriate appropriately so, to make hypotheses, test them, no hypotheses, etc. But this is different, and I think has a potential to be quite complementary to traditional methods in social science. So another symptom of being a physicist is you first want to know, how big a problem am I talking about? And so I tried to do some simple estimates, back of the envelope as we call them, of how much data are we talking about. It's really information, not data, but I'll use the words here interchangeably. If you take a dense urban environment, 10 kilometers in radius, there are about 3 million people in that area. They live in about 1 million households, work in about 300,000 businesses, and there are about 500,000 vehicles. So let's do the data rates. The data rate is dominated by personal data, position, physiology, and psychology. For people, that turns about 20 bytes every 5 seconds or 12 megabytes a second data flow. The transactional data are far less frequent. You don't make a phone call or purchase something with your credit card as often as you just move around, so that's a small number. If you want to measure sound, which is an object of great interest to us in New York City, at 100-meter spacings and a kilobyte per second, it's about a kilobit per second, it's about a megabyte per second, so again, small potatoes. Altogether, it's about 20 megabytes per second to cover this kind of city, 600 terabytes of storage, which you can store for less than $100,000. So the notion, as the minister alluded to, of can you know everything and know it in almost real time, the answer is it's quite conceivable. The challenge is to A, realize that, and B, what do you do with all of that data? So let's look at data sources for a minute. There are organic data flows, the administrative records, the operational records that the city has. These days we have social media, Twitter, blogs, Facebook. We have sensors. The proliferation of sensors has already been mentioned, but not only the phones that we're carrying, but portal sensors for people and vehicles. I'm sure there's a light sensor and a temperature sensor in this room, which is on the net as well. And then finally, there are opportunities for novel sensor technologies, which I'll show you a bit about as those of us from outside the field start looking at these problems. So what I want to do now is go through a list of points about what it takes to do urban data. And I'll go through these one by one with brief illustrations of each. And let me start multi-sector collaboration. For most academics, for most governments, this is an unnatural act. We all have different goals. The academics are different than the industry, is different than government. Putting this all together is a challenge. Not impossible, but you have to work at it. At CUSP, we have university partners in the US and abroad. We have industrial partners. Some of the big names are listed there. We have involved the US national laboratories, which have a great resource in computing, modeling, and sensor development. And then we are partnered with the government agencies concerned with the city of New York. That's absolutely essential. This has to be done in collaboration with the government, preferably a unitary government, which is an example, which is a circumstance you benefit from here in Singapore. If you go to Los Angeles, there are 50 different municipal entities in the Los Angeles area. London, 30 or something like that. New York City has one unitary government, at least within the geography of the city, covering 8.5 million people, so it's an advantage. The second is that this is a multidisciplinary collaboration. I like to say in CUSP we need to go from censors to sociologists to civil servants. You need to embrace all of those disciplines if you're going to do something that has an impact. This is not just about writing papers, nor is it just about achieving some particular effect in the government. The way we organize our research program is to, along the vertical axis, have a set of data disciplines that range from sensors to database curation and creation to GIS, to modeling capabilities, machine learning, and along the horizontal axis up the top, different urban domains, and then we matrix those skills on the left with the domains on the right. building upon several user facilities, which I'll describe for you in a moment. It also requires, to do urban data, you also need to acquire, integrate, and exploit large, diverse data sets while respecting privacy. We are creating in New York City, and there are a number of other such activities in other cities in the U.S., a data warehouse facility. This is about the omnivorous ingestion of all manner of data about New York City. It's a challenge to make the data sets interoperable. For example, in New York, there are 5 different ways of designating a particular building. You also need multi-layered access protocols so that you don't violate privacy or security considerations, which have already been mentioned, a very important aspect of the warehouse. We start with data from the city agencies. We're generating some of our own data sets, and we're making sure to build in these important safeguards as we go through it. Here's an example of what New York City has done. This is the Data Bridge data set that was assembled during the last 4 years of Mayor Bloomberg's administration by a guy named Mike Flowers, who is now working with us. And you can see it takes data feeds from many different municipal agencies. In the upper left, Department of Transportation, moving around clockwise, finance, sanitation, buildings, et cetera, et cetera. It was a major achievement of city government to get all these data sets in one place. I like to say that the second most basic human urge is to hoard data. The academics do it because they need priority in writing papers. The government does it because data is power and prestige within the government. And the companies do it because data is valuable. And so we need to, as the minister remarked, we need to break that mindset in some way, or provide the technology that allows sharing while respecting those considerations. Privacy has also been important, and it's an important area of research. We sponsored a book that was published back in July by lawyers, ethicists, and computer scientists of how you do privacy in this era of big data. The ability to create new data streams for a scientist, again, is one of the most interesting aspects of this business. I want to give you 2 or 3 examples of what we're doing at CUSP. New York City makes available the taxi records of every cab in the city. There are 13,000 taxis that make 500,000 rides a day. We have now 5 years of such data, start and stop, time, fare, tip, medallion, driver, and so on, for every cab ride in the city. And it's possible, as 2 of our researchers, Claudio Silva and Juliana Ferreira, and their collaborators have done, to drill into the data and start to learn interesting things. In this case, they looked at 1 week in May 2011, 3.6 million trips. They looked at trips starting from the train stations, 2 in New York City, and the 2 airports, LaGuardia and JFK. And you can see in the upper panel, over 1 week, the number of trips per unit time from the airports and from the train stations, and the tips per unit time in the lower panel. And the pattern is surprisingly repeatable. It's a pulse of the city kind of measure. We'll come back to that in a moment. And not surprisingly, there are more tips coming from the airports than from the train stations. But you can then start to do behavioral studies. Are the tips larger when the trip ends in a rich neighborhood compared to a poor neighborhood? Are the tips greater when the sports teams are doing well and people are feeling optimistic? It's actually true. Et cetera, right? So there's interesting behavioral data. One thing we've been doing at CUSP is to look at persistent granular imaging of the city. These are 3 pictures taken roughly 30 seconds apart from our offices in Brooklyn, looking at Manhattan. To orient you, you can see the Empire State Building in the left, and these are 3 frames that are nominally identical. And what's interesting is to flip through those frames and look for differences. Of course, you will see the traffic moving in the lower part of the image, but if you look carefully, you can see in the middle of the image a plume coming out of one of the buildings. suddenly we've got a way of looking at, in this case, 800 buildings at once, in real time, with a cheap sensor, a camera no better than what's in most people's phones, and watching and understanding, in this case, an environmental issue. Here's a time lapse, and you can see the plume coming out from the center. It's even more visible when we subtract the background, as in that lower panel. This is the difference from frame to frame. You can see the plume coming out, and we've colored it in the upper right. So once you see that plume, you can start to ask what buildings are emitting, where is it going, what are they emitting, who's getting exposed, what quality of heating oil are they using, and things of that sort. Here's another example. Again, persistent synoptic imaging, doing from an urban vantage point what you would do from a satellite, but much cheaper and much more effective. This is a thermal image of a slice of New York City, and you can, in that building, read the thermostat setting of every apartment. And in that building, we know there's a data center, so it's hot on the bottom and hot on the top and cool in the middle. And that building is public housing and has a rather poor heating control, so the heat's turned up and everybody's moderating the temperature in the apartments by opening the windows. Persistent, synoptic, granular. You don't need anybody's permission to do this kind of data. It's not perfect, but one has got correlative data for all those buildings, and you can start to complement the more detailed data that one has. Deep study of millicities is another thing that we think is important, in just the same way that a neuroscientist would take a square centimeter of cortex and try to instrument every neuron to understand what's going on in the bigger brain. We'd like to take a community and fully quantify it. We're partnered with the Related company who are developing Hudson Yards in Manhattan. This is a development of over 5 million square feet, and we're looking at how you would instrument that development. You want to know about resource consumption, air quality, et cetera, in the buildings, all the infrastructure, safety, security, environment, and people. And being able to create this kind of almost laboratory of intensively instrumented chunk of the city, probably about 10,000 people here, looks to be a very attractive way to proceed scientifically. Students are really important. Students, as we always say in the universities, are the future. It's really true here. We are running a master's program. This is the second class. There are 63 students in the class. And what's interesting is some of the statistics. Where do they come from? They come 10% from business, 30% from engineering, 13% from computer science, 22% from the social sciences. Promoting this dialogue between the social sciences and the more technical data disciplines is one of the very important things to be doing, but is frankly one of the most difficult to do. And the students are doing that. They're much less set in their ways than we older folks are. It turns out also this subject, as a STEM subject, is very attractive to students. When I was going through early education, if you were good in mathematics, you became a physicist or economist or something like that. These students have a much more social bent about them. They want to do some good for society, and being able to do that in a quantitative discipline is something that's very attractive. Finally, a willingness to get one's hands dirty. Universities are traditionally ivory towers. Academics tend to look down upon anything that might have a hint of practical application, or at least used to. It, of course, varies by discipline, to be fair. But we're executing a great variety of projects for the city and state. Detailed economic mapping is something that many people are interested in. New business creation, job creation, tax revenues. Things as prosaic as how many bus drivers need to be called in every day by the bus authority to make up for people who are sick or don't show up. Parks, how many people use a park? What do they do there? You can go on and on with the applications. Many of these are executed in close coordination with the city agencies in New York City. Let me close with some thoughts about science. I focus mainly on applications, but there's science here to do as well. And one is, in my view, can we document the pulse of the city in its various dimensions? I show you on the left the number of taxi rides per day in 2011 and 2012. You can see the weekly pattern. We've talked about that a bit already in the train stations and airports. On the right, I show you the pattern of roughly 20,000 nights that we observe at once in a city view. They go on and off with some regularity during the night, but there's a pattern that's different in the weekdays than in the weekends, and you see anomalies in these patterns. So, what's normal for all of these indices? What's the variability? Are there correlations among these metrics? How do they respond to perturbations? How predictable is the city in its various dimensions? Can we develop something like a weather forecast for the city, saying economic activity will be 2% higher than normal tomorrow because of X, Y, or Z? And how accurately can you do that? And then finally, the last science question is, how does the macroscopic behavior of the city arise from the many microscopic decisions that people make? The physical structure of the cities, can we use this to input decision rules into agent-based models? What's the role of geography, culture, and policy? I think with that, thanks for your attention, and I hope I've simulated some thoughts that we'll get to during the discussion. Thank you.